Sure.
There we go.
Okay, so the title of my talk today is How Fast Do Submarine Fans Grow? Insights from the Quaternary Golo System of Offshore Corsica. And this is work I did when I was working at Exxon Research, and I've continued in collaboration with my friends and colleagues, Gladys Gaillot, Tammy Rittenauer, Kate Love, and Mike Bloom. Okay, wait, okay. So the rates of deposition in terrestrial and shallow marine environments have been quite well constrained using optical stimulated luminescence, OSL, carbon-14, and other age dating techniques. And so if you look at this kind of classic paper by Mayel from 2015, it's able to show rates of instantaneous rates of sedimentation versus the time scale of different processes for a variety of shallow marine and non-marine environments. So the question is, how do deep water environments compare with these well-established rates for things like rivers and deltas? And to date, the rates of deposition deep water are much more poorly constrained and less well understood than in shallow water and terrestrial environments. This is because it's very costly to sample. You need to use a drill ship or research vessel. It's very difficult to monitor active processes on submarine fans because they occur kind of episodically, and also they're extremely powerful, which makes it difficult to monitor. So, unlike, modern fluvial or terrestrial or shallow marine environments when we can easily go out and measure things like bedform migration, for example. Also, optically stimulated luminescence, which fills in a key time gap from about present day to about 150,000 years ago, has not been widely used on deep water sediments for reasons I don't quite understand. So generally, things like ocean drilling program cores and all that are dated using carbon-14, which is only good for about the last 40,000 years. Though, in this study, we used OSL quite extensively and it had good results. This is important because submarine fans encompass some of the largest sedimentary environments on Earth. For example, the Bengal fan, which is the largest sedimentary environment on Earth. And they're important recorders of sediment flux and climate. So if we think about deposition rates on the bed scale, we're just in the last few years have started to get better data on the duration of flows, turbidity current flows in submarine canyons. And this is because better technologies become available to monitor these flows in a number of submarine canyons where there's active deposition going on. For example, Monterey Canyon, the Bar Canyon in France. Oceanographers have put instruments in the submarine canyons, and in the past, in the early days, they used to attach these things like current monitors and sediment traps to the seafloor, where they were almost invariably destroyed by turbidity currents. Nowadays, the technology, the idea is to suspend the sensors above the submarine channels and using things like acoustic Doppler sensors to measure current velocity, then you'll be able to get good records of these flows without destroying the instruments. Or some of them are attached to the seafloor with flotation devices, so when the flow comes through, they can gather data and then float to the surface where the data recorders are captured by ships. And as a result, and you can see this paper was just published a few years ago, Zabala, they've worked on Congo Canyon off the coast of Angola. And you can see here in blue, it shows these very long duration flows that they've been able to measure that go on for 5 days to a week, occur once or twice a year, associated with floods in the Congo River. And they achieve current velocities of up to 8 meters per second, run out lengths up to 1,000 kilometers. So they put these sensors at multiple locations along the Congo fan. So this is in a passive margin system, kind of very mud-rich turbidity currents that last, as I say, for up to a week above the threshold velocity to transport sand. Some of these systems like the Monterey Canyon, they're much smaller systems and active margins, and the flows may be triggered by events like typically storms that deposit a lot of fluvial sediment at the head of canyons, or sediment moved by longshore drift at the head of submarine canyons. And you get flows that last for, you can see the scale here in hours for, 10 hours or so, or a few hours. So in any case, when looking at, if we look at, so this is a turbidity current deposit, one bed from the Lyceum Formation in Southern California. So it's a couple meters thick. You can see these large mud clasts and even a big granite boulder here. We would, based on these data from modern systems, we would imagine that on the bed scale, deposition of an individual turbidity current might record something like a few hours, or maybe, you might see multiple beds in the case of these flows in the Congo fan. With deposition, very high local deposition rates in the parts of the canyon that are being eroded, rates of erosion, and then deposition on the very active parts of the fan. So locally high rates at the kind of bed scale. Oh, wait, sorry. Okay. So, kind of moving up in the stratigraphic hierarchy, if we think about what rates are going on at the scale of architectural elements, so fan lobes, levees, channels, there's not a lot of data on this. Probably the best work was a paper in 2006 by Maslin looking at the Quaternary Amazon fan, where they were able to do an extensive carbon-14 dating effort on ocean drilling program cores on the fan. And they will work out a stratigraphy. You see there's these very thick levied channels that can be up to 100 meters thick. And each of the different colors shows a different one of these channels. And so you see the kind of main channel feeding out of the Amazon Canyon, and then channels avulse through time. And so you can see, for example, this green channel. So a degree of latitude at this, it's near the equator, is about 111 kilometers. So this green channel extended over 100 kilometers, and you can see here's the time scale in about 4,000 years. And so each of these kind of channel avulsions occur on the time scale, sort of 3,000 to 4,000 years. So we can get extension of these bodies on that sort of scale. So, if we look at ancient deep water deposits, fans, so this is the Karoo and Permian in South Africa. You see these individual elements of a submarine fan here, these sands that might represent maybe deposition on the scale of a few thousand years. And we're going to kind of, we actually have data from the Golo that'll help understand, allow us to quantify that more. I think one thing that's really important to keep in mind with systems like the Amazon is that they become inactive when sea level rises. So you can see here that sedimentation really shut down about 12,000 years ago, and it's just being draped with very fine-grained carbonated and organic rich sediments. So you have instantaneous high rates of deposition on the active part of the fan, and the rest of the fan, laterally is inactive, and then through time there are periods when sea level is high and deposition becomes inactive. Then if we look at the scale of entire submarine fans, again, it's kind of a limited amount of data, but work done by our colleagues at Ephemer in France on the Congo fan, for example. So here's the coast of Africa, it's Congo, Angola. You can see this very large submarine fan, 100 kilometers, 100 kilometers for scale. The submarine canyon actually attaches, goes into the estuary of the Congo River. So even though sea level is currently high, the submarine fan is active. And the current monitoring data we saw came from a series of monitors deployed along this active channel of the fan. And there's distal lobes here, and there's data from a variety of sources indicating that deposition is occurring now on the distal lobes, even though they're almost 1,000 kilometers from land. So we know from ocean drilling program information that the Congo fan began to form about 790,000 years ago. It's an average of about 2 kilometers thick in that time. So that gives you about 2.5 meters per 1,000 years deposition rate on the average. Of course, it's locally much higher along the active channels. So to address some of these issues, there's a joint research project with between ExxonMobil, IFEMER, which is a French oceanographic lab, Institut for Recherche de Exploitation de Mer, in Brest, France. They provide the research vessels, Total E&P, and as I said, Exxon Research. So we had a 2-year research program that involved in the first year acquiring high-resolution seismic data and bathymetry over the Golo fan, which is on the east coast of the island of Corsica. And this is an area that IFEMER has worked for many years and had a good understanding of the geology based on past cruises. We simply went in the first phase of the study and shot a much tighter grid of multi-channel 2D seismic data. In the second phase of the project, we used a drilling ship provided by Fugaro to drill 5 long cores, 2 on the shelf here, and 3 across the submarine fan, 1 on the slope, 1 you can see here, there's a submarine canyon, submarine channel, these lobes related to different periods of deposition. We'll come on to that later. So we drilled 1 core on the slope, about mid-slope position, where we expected to get a very complete stratigraphic record, 1 at the channel lobe transition of this active channel, and then 1 at the distal end of this submarine fan complex. And the cores, we of course gathered the usual sedimentologic data, and the cores were dated using optically stimulated luminescence, OSL, carbon-14, and also oxygen isotopes. So we were able to get a very good stratigraphic record going back to about 400,000 years before present. This shows kind of the chronostratigraphy. So we had this grid of seismic data, and we were able to map key seismic stratigraphic surfaces across the basin, calculate sediment thickness. We calibrated the seismic data using the core to understand the distribution of sand and mud. And then we were able to use for older dates, we were able to match to the global oxygen isotope curve. And for younger dates, younger than about 100,000 years before present, we used a combination of OSL, shown here, and carbon-14 for the last 40,000 years to date the sediments. And we were able to relate deposition on these submarine fans to the global sea level curve, shown on the lower level here. And you can see that, when we had there's periods of high sea level, shown here, the kind of odd number. These are these events here shown in white, periods of high sea level, which correlated to the deposition of these carbonate-rich marls and essentially no deposition of sand. As sea level dropped, shown here in the colors, so this is marine oxygen isotope, going into marine oxygen isotope stage 2, the last glacial maximum at about 25,000 years before present. We started to see deposition of sand, and as sea level rose, that shut off, and mud and carbonate-rich material were deposited across the fan. So we're able to relate sand-rich deposition to these glacials, periods of low sea level, and basin-wide distributions of mud and carbonate to periods of high sea level. Now, this is not in itself a terribly surprising outcome. I mean, you predicted by sort of classic sequence stratigraphic models. But we were able to use these data and the thicknesses that we mapped from the cores and seismic to come up with rates of deposition, both kind of instantaneous rates of deposition at the wellbore, the core location, and average rates of deposition across fans. So these are a series for the last, kind of 5 glacials or periods of low sea level. These are thickness maps, and you can see here. So this is bathymetry. You can see the continental shelf and these 2 submarine canyons, the South and North Golo canyons, that feed sand from you can see there's a series of deltas fed by the Golo River, where sediment is fed across the shelf when sea level is low through these canyons, down through a series of channels into a series of submarine fans, shown here. It's kind of thick patterns, bullseye patterns. Each of these deposits the kind of blue purple colors here are about 100 feet, 100 meters thick. But of course they can, you can see you get very, locally, they're much thicker in some places than in others, and on the margins they're, sort of 10 feet thick. So there are two processes going on here on this sort of time scale, 100,000-year time scale. So you had sea level rising and falling, and sea level rose. The deltas backstepped across the continental shelf and severed the connection between the fluvial deltaic source of sand and mud and the canyons, and especially, I would say, especially sand. When sea level was very low, there's a river, the Golo River, fed directly into the head of some of these submarine canyons. We're able to map that. And as sea level rose, you first shut off deposition of sand, and as sea level continued to rise and the deltas backstepped across the shelf, eventually, mud deposition continued, but at lower rates, along with carbonates. And so you can imagine, and then there was a kind of autocyclic process of this river, the Golo, shifting back and forth across the shelf when sea level is low, activating one or the other of these canyons. It's pretty clear from seismic mapping that the northern fans are not active at the same time as the southern fans. So when this fan was active, you were depositing a veneer of mud out here, and when these fans were active, this area was being blanketed with fine-grained sediments, which have a unique seismic facies. So if we look at deposition rates, this is, marine oxygen isotope stage. We have the kind of duration, sediment volume in cubic kilometers. So for example, during marine oxygen isotope stage 1, which is what we're now as sea level rose, you can see there's a fairly thin veneer of sediment, only a couple of meters thick, but is deposited across the entire basin. And it's got a unique high amplitude continuous seismic facies, which based on our well data, we relate to mud and marls. So you can see we had a, kind of mud deposition rate in both volumetrically in cubic kilometers per 1,000 years and vertically in meters per 1,000 years, kind of average rates. And so I think, kind of an important thing to take from this lot of data is that when sea level is low, like marine oxygen isotope stage 2 through 4, is really when we start to see sand deposition. We really don't see sand deposited when sea level was high. The volumetric, if we look at the total sediment rates, they vary by a factor of 2 or 3 between sea level high and sea level low. So, a large amount of mud being deposited here, but the difference is largely driven by the fact that when sea level is low, you had a substantial sand volume shown here. So that was kind of, that was an important finding, that the sea level, the deposition of sand on the submarine fan was extremely sensitive to sea level change, whereas deposition of mud continued to go on, kind of regardless. And so we had this sort of 2 to 3 times difference in sediment volume on the fans, depending on sea level. Now, at a finer scale, within these submarine fan lobes, so we had, for example, over the last 25,000 years, there were 2 lobes of this southern fan that were active. One during MIS-4, about 50,000 years ago, and one during MIS-2, and then actually had sort of a shutdown of sand deposition on the fan during MIS-3. You can see that we were able to use seismic facies to get a good estimate of sand versus mud content away from the well bores. So we had this kind of high amplitude continuous seismic facies, which was the mud and marls, low amplitude continuous, which is just the mud. It's the marls that give you the impedance contrast. And then this high amplitude discontinuous seismic facies, which is the sand-rich facies. So we're able to map the distribution of these seismic facies as a proxy for sand and mud distribution. So at the time scale, at shorter time scales, when sea level is low and these fans were active, we saw a large scale avulsion of elements of the fan, in which we were able to map on seismic data. And you can see here these different lobes that were deposited as you had this main feeder channel, as you had an avulsion across these different elements, stratigraphic elements across the submarine fan. So this was going on kind of, and I'll show you some data on much shorter timescales, on the sort of, timescales of hundreds or a few thousand years, whereas the whole fan was deposited in a matter of 4,000 or 5,000 years. So if we look at our core data, so this is a core on the slope, and you can see here we've got, this is median grain size, from cores, and then this is calcium content. So you can see the marls show up as these blue peaks, and we've kind of infilled it with brown is mud, and yellow is sand. But this is all based on laser particle size analysis on the kind of centimeter scale. So you can see this. Here we are on the slope. Just mud and marl deposition through this time. It's away from the main axis of sand deposition. This core was cut at the mouth of a levied channel that fed into these two lobes. And so, that's here. So this is kind of at the up dip end of this lobe. About 25 meters of sand were deposited in about 3,000 years based on our OSL dates from samples in this sand. So you can see that, this is quite a thick sedimentary body, locally very high deposition rates of 7 meters per 1,000 years. And this just shows kind of our distribution of carbon-14 and OSL dates. This core was taken at the distal end of the submarine fan, and it was all deposited during oxygen isotope stage 2. And so you see deposition started about 35,000 years ago and ended about roughly 15,000 years ago. Sand deposition shut off, and you went to a kind of a thin veneer of mud. So if we look at these data, it's more detail. We can see, that for these larger features, the North and South Golo lobes, they had areas of hundreds of square kilometers, were deposited over periods of, say 20,000 years, sediment volume of, 2 or 3 cubic kilometers, mean thickness of, 15 to 25 meters. So in an outcrop, these would be substantial bodies, right, that you could map. And we get kind of aerial distribution rates of, a meter per 1,000 years, volumetric rates of average rates of kind of a tenth of a kilometer per 1,000 years over in these lobes. Now, as we break them down into finer stratigraphic units, they're obviously much, so these are all deposited in this South Golo complex during marine oxygen isotope stage 2, so in the last 25,000 years. You can see, again, they're fairly, large bodies that span, tens of square kilometers, and mean thicknesses of, about 10 meters. And you get a sense of, much locally, much higher deposition rates, 10 meters per 1,000 years, especially at the kind of where the sample happened to fall near the channel to lobe transition. And, this is not terribly surprising. We know from this idea of Sadler's law that, generally in the stratigraphic record over shorter time scales, you see higher rates of higher sort of instantaneous rates of deposition. Of course, this whole submarine fan is currently undergoing, quite slow rates of deposition. So if you were to average it over longer time scales, over millions of years, the rates would be much lower due to this Sadler's law phenomenon. And this compares with some very interesting data that was gathered by our colleagues at IFAMIR on the Congo fan, the active lobe of the Congo fan, where they were able to use cesium isotopes, which come into the atmosphere from the atomic bomb testing that was done in the 1950s through, I think, early 70s. And so these sediments are, have literally been deposited in the last 50 years. And they were able to get, locally very high rates comparable to the rates we measured and even higher on the active lobes of the Congo fan, which is a much larger submarine fan. So, I mean, there's very little of this kind of data in the literature. And I think that's kind of the significance of our work, and certainly of our colleagues at IFAMIR for doing similar kind of analysis. I think the main thing this study contributes is we're able to map these bodies using a fairly fine grid of 2D seismic data. So we know something not just about the instantaneous deposition rates at an individual core hole, but we know something about the distribution of those bodies laterally and how their thickness changes. So in conclusion, so the kind of opening question was, how do submarine fans fit into this graph of terrestrial depositional systems? And I think the answer is that, we see rates of deposition and timescales of deposition of bodies of similar size that are as high or higher than we see on, say, in river channel belts or in active river deltas. And, maybe that should not come as a big surprise, but, I think that's a significant part of our finding. And I think for a long time, we've had a kind of view that submarine fans were largely, inactive or active only very episodically. And I think we're starting to see there's much more active deposition going on in some of these systems at rates that are comparable to very active parts of a river delta like the Mississippi, or a channel belt like the Mississippi, for example. So submarine fans are dynamic environments with sedimentary bodies tens of kilometers across, tens of meters thick, that were deposited in less than 20,000 years, in some cases less than 5,000 years, levee channels that can extend kilometers in a few thousand years. So rates of submarine fan deposition, formation of major architectural elements are comparable to those seen in key elements of fluvial and deltaic systems. Oops. So I'd like to acknowledge my colleagues at ExxonMobil, Total, and IFAMIR, and also those three institutions for funding the data gathering part of this study, the two cruises. Gwenel Jouet and his colleagues at IFAMIR for their outstanding job of data acquisition and for sharing their knowledge of the Corsica Basin. We've published the results of these studies most recently in a paper in October in geology about the rates. There's a longer paper in geology 2 years ago with our colleagues at IFAMIR about the whole about the entire system that was published in GSA Bulletin. Thanks.
Awesome, thank you. If anyone has any questions, feel free to unmute yourself and ask. I guess I have one.
Sure.
So Corsica itself is kind of a smallish island in the Mediterranean. How would you expect, do you expect the depositional timescales to be different off of larger fans? Like you showed a submarine fan off of the Amazon at the beginning.
Right, yeah, I think that's a good question. I mean, we're seeing, if we look at the Congo fan is probably the best studied in terms of, this kind of rate issues. And, we're seeing rates as high or higher on the active parts of the Congo fan. I think the big difference with the Congo fan is because it's got this submarine canyon that's connected, that is cut right up into the estuary of the Congo River. Deposition goes on continuously regardless of what sea level is doing. So if you look at kind of rates of deposition of the whole Congo fan, it would be much higher for that reason alone. It doesn't have these kind of slowdown periods that you see, say like on the Amazon fan or the Golo when sea level's high and the shelf's drowned. But certainly, we see the rates of kind of extension of those levee channels on the Amazon are really dramatic. And, when sea level is low, the entire sediment load of the Amazon River appeared to be passing down onto the fan. And so there I would expect even probably higher rates of deposition locally than we saw on the Golo, because it's a much, much larger depositional system.
Cool, thank you.
Okay.
Hey, Mike, I had another question.
Sure.
So, you know, when I first started studying deep water systems, the beef or the conventional wisdom was we couldn't have equilibrium bed forms like cross beds, um, like that, because the length of these turbidity flows wasn't long enough. You think your work has changed that perception?
Well, I don't know about, I mean, I think the work that this group, Peter Tailings at Southampton are the ones that are doing the current monitoring in the Congo Fan. And the fact that you have flows that are above the threshold velocity for sand transport that go on for days, it should be comparable to a flood in like the Brazos River or something. And certainly, I don't think anybody doubt those are equilibrium bed forms in a river, right? Given that through a time scale. I think the big difference is there was this notion, I think, that you're referring to, that deposition, turbidity current deposition essentially maybe occurred for minutes, above threshold velocities. And that in those short time frames, you couldn't come into equilibrium with large bed forms. But I think we're starting to see from this current monitoring data that some of these flows can be quite long-lived. And of course, there's been the observation, we see these very large bed forms, both in outcrop and from seafloor imaging.
Yeah, thanks. I had another question about the bomb cesium. So when I did my dissertation on the Texas shelf, we found that bomb cesium layer,
Oh, right.
Which one you use, 1964, the Test Ban Treaty. And, it was buried just, a matter of 30 millimeters into the substrate. How deep is that surface in your stuff?
Well, we didn't do that. The folks on the Congo, I think it was down like a meter or more. I mean, so the cores out there are really spectacular. It's very coarse grained sand, 1,000 kilometers from the shoreline, full of organic material. And I think like Ephemer's even found things like plastic and and stuff in these sediments out that far. So they're really robust beds, and they were able to document, based on repeated side scan sonar, evidence of erosion and deposition from individual flows that were sort of 3 to 5 meters. So, really, these are really powerful flows that could move like cubic kilometers of sediment in one event.
Thanks.
Okay. Well, thanks very much, Aaron.
Yeah. Thank you for your talk, and round of applause virtually.
Okay. All right. Take care.